Amazing. So thank you so much, Jack, for coming in. I'm going to stay seated as I've hurt my back. But let me introduce you again. Dr. Jack Holguin is an early career fellow funded by the Leverhulme Trust at the University of Manchester. Previously, Jack was a postdoctoral researcher at École Polytechnique in Paris after completing their PhD at the University of Manchester. Jack works on a range of topics related to quantum fluid dynamics, contributing to studies on QC factorization, the development of the Holguin event generator, and the application of jet substructure to heavy ion physics. And we're delighted we have an opportunity to hear about collinear factorization and the fact that it does break even in the optimal simple observable. So Jack, please take it away when you're ready.
Yeah, thank you very much. So as Will said, I'm going to talk about how collinear factorization breaks. And the goal of the talk really is to discuss three main points. Firstly, it's to introduce this observable known as the jettiness, which some people have referred to in the literature as an optimal simple observable, specifically for tagging the number of jets in an event. For instance, let's say you wanted to find a Higgs decaying to two bottoms. That should be a two-jet event. Very commonly, jettiness is a sort of observable that should be used as a discriminator to identify that event versus other things. Once I've introduced jettiness, I'll discuss how it can be computed using a tool known as the Lund plane. And then I'll pause that discussion for a little bit to discuss factorization breaking more broadly, in particular, giving the prototypical example of an observable known as the gaps between jets observable. And then I'll put both these points together and discuss the factorization breaking in the one jettiness observable. So what is jettiness? Well, its precise mathematical definition is given on the left here. So this is the definition, and then you produce an observable by integrating a differential cross-section against a delta function which constrains the momenta subject to this definition. It's understood, it's quite simple though if we understand it diagrammatically. Really, what it requires is the n jettiness has n jet axes plus 2 for the initial beam axes. These can be found via a variety of means. You can typically try and use an optimization procedure to find the jet axes, such as in thrust or something like that. But here, I'm just going to assume the jet axes are given throughout this talk. So in this diagram, for instance, on the right, I've used blue particles there, the incoming particles. So they would be stuff coming from a proton. That produces a hard collision, producing 3 outgoing particles. And so altogether, you've got 3 outgoing axes and then 2 axes for the beam. And then these radiate as well, which are all these green gluons. And the jettiness is requiring that the sum of the longitudinal momenta pointing down each of these axes is less than a particular value. So, sorry, by longitudinal, I mean the light cone momentum down this axis. So it makes it saying that everything is very collimated, which is what I've drawn with these discs. This is like we collate all the radiation going along n, and look at its light cone momentum down the direction n. If it's fully collimated, that will be 0. And so the jettiness will give you a value of 0. If it's very diffuse and going off in all sorts of directions, it will be much larger than 0. And this was introduced by Stuart Tachman and Volta in 2010. Okay, so I'm going to focus on just the one jettiness observable. So this is an observable where we've got 2 protons coming in, and then it produces a single jet coming out and an associated recoiling neutral particle, such as the Z boson. And we're looking again at the total amount of light cone momentum going down each of these 3 axes, so the beam line or the aligned with the jet. And I'm going to, for concreteness in this talk, always consider this topology where the protons coming in contribute a quark and a gluon. So this one's producing a quark, this one comes in producing a gluon. And that they scatter to produce in the middle here, we've got a virtual quark, and then that radiates a Z and produces a quark in the outgoing state. And that quark in the outgoing state is our jet. Okay. So how do we compute this? Let's look at this at one loop. And doing so is easier to look at the cumulant. So we integrate over the values of the jettiness up to some cut, which I'm calling tau1. And doing so turns the delta function in the differential distribution here to being theta functions. And it's basically asking that we're inclusive of everything less than some value of jettiness. So we're inclusive of everything that's perfectly collimated down the three axes up to some cut. And doing this at first order in alpha S takes the following form. So there's two contributions. You have to integrate the cross section for a quark and a gluon scattering to produce a quark and then a gluon, which was additionally radiated, plus the Z, with a requirement that the jettiness is less than some value tau1. Or you can have a loop. So the Born process, the quark and a gluon goes to produce a quark and a Z, and that's dressed with a loop. So I've got that diagrammatically down below here. On the left, we've got its radiated gluon. On the right, a loop is dressing it. Now, on the right term, this actually always has a value of jettiness is 0 because everything's perfectly collimated down those axes because there are only 3 particles. And so we can ignore the theta function, and the calculation becomes integrating where this green gluon is allowed to go subject to this theta function constraint plus the loop contribution. Okay, so refresher from last week when I discussed the collinear factorization of amplitudes to get the DGLAP splitting functions. We can do this calculation if we only care about getting the leading piece from the collinear limit, where this green gluon is very collinear to its parent, by factorizing the cross-section in terms of the cross-section without the gluon, times by selection of collinear splitting functions, where we need to sum over all the possible legs that the gluon could come from. And this is what's in the top line. You have, this is a splitting function for a quark, it going to a quark, so it irradiates a gluon. So this would be if the green one was off the initial state here. This is one, the same again, because it's a quark going to a quark again. So this could be off this gluon here, so this quark here. And this is a gluon radiating. So this is if the gluon came off this leg here. And so we add the 3 terms together. And then the loop contribution is the exact same, but with a minus sign, and we've got to integrate over all the momentum that could be running through the loop.
I'm sorry,
right, so let's,
a dumb question. So why are you requiring there be a gluon at all in the final state or as a loop in the final state? Why not? Could I not consider a quark glue goes to quark plus Z with nothing else?
So yeah, so that is what's in. So can you say your question again? Sorry.
Yeah. So wouldn't the leading order contribution be the bottom line, but without the gluon loop?
Yes. Yeah. Exactly. It would be. So I'm specifically trying to compute the one loop contribution.
Oh. Okay. Okay.
Yeah.
Sorry.
To do this. Your contribution that you just said is actually just going to be equal to the cross section for the observable, right? Because it's always passes the cut. Mm-hmm. So it's just the cross section to produce a quark and a Z from the quark and a gluon scattering. That will turn up in a couple of slides' time when we add everything up. But I'm specifically isolating to the one loop contribution right now.
I gotcha. It's so easy you didn't even bother. And I'm just too dumb to realize that you're just so smart.
No, it's just in this situation, the answer's effectively 1.
Yeah, no, it's good. Okay, super. Thank you.
Yeah, so okay, so let's simplify this calculation down in a way that's going to help us in the later slides, because this currently looks a bit complicated, by approximating all these kernels, these splitting functions. And if we do that, we can write the entire cross section as equal to this. So we have this dkt over kt here. That's just a log transverse momentum of the emission. So I've got my little diagram down here reminding you what kt is. It's the transverse momentum relative to the parent. And then we can swap out z, which was the light cone fraction that the emission had of the momentum, with the angle it was emitted at. I've got the change of variables written down here for you if you're interested. And that actually also then simplifies if we keep only the leading piece to being a log theta. And then we have all the color factors from the different contributions, which I've labeled here. So you've got an alpha S times a fundamental Casimir is a radiation off a final state quark, or an alpha S fundamental Casimir off the initial state quark, or an adjoint Casimir if it's off the gluon. Okay. And this is where we see the double logarithmic singularities I discussed last week, because if we were to integrate over this entire phase space with no cut, we've got two log integrals, so you'll get two log singularities.
I'm sorry.
Now we can.
So here's another question. So the leftmost diagram in the middle, where you've got the green coming off of the black, that I would see as having soft and collinear divergences that are going to lead to a double log. But the gluon coming off of the incoming things, that's going to be in a totally different direction than the outgoing black line. So I would have expected those to be finite, not to have.
Yeah. So this gluon off the initial state gets
Yeah.
its divergences by being collinear and soft relative to the blue initial state particle.
I agree. Very good.
So this KT is contextual. It's always the transverse momentum relative to its parent, not the beam transverse momentum or something like that.
So you've done some fancy footwork of redefining what your coordinates are.
So KT is always defined as in this box here, that it's always relative to the parent particle, and so is the angle.
Got it. Thank you.
That will turn out to be an important point in the latter calculations, actually. So it's good to stress that these are relative coordinates, effectively.
Got it.
For decomposing the momentum. Okay, so with this, we can now plot this phase space that we're going to integrate over, because the actual matrix element that survives is just a constant. So we can understand the entire phase space we're going to integrate our observable over by just plotting the log KT and log theta plane. And that looks like this. If we put a minus sign in, so it's log 1 over theta, so that it's then approximately equal to the rapidity of the emission in the from respect to its parent, then the phase space looks like this. So we've got log KT down the y-axis. As KT goes to 0, we go to negative infinity. We've got log 1 over theta on the x-axis. So as theta goes to 0, we go to positive infinity. And the region where you are allowed to have a particle be emitted into is given by this yellow boundary. So a fixed value of KT and theta is just a black spot on this plane. So that would, and we integrate over this plane. Now, what this boundary is, this yellow boundary, this is given by the line log KT is equal to log theta. And within the small angle approximation, that's equivalent to the constraint that the emission, the emitted gluon must have energy less than its parent gluon, otherwise you'd have violated energy momentum conservation. So that's what this yellow boundary is. So you can only integrate in this region. And then if we label the sorts of properties an emission will have across this plot, if it's near the yellow boundary, that's meaning it's going at a small angle is allowed by the momentum conserving constraint. And so that's the collinear region going along this yellow boundary. Down the y-axis, that's saying it's at mid angles. It's not at all collinear, but it is potentially going to be very soft as the KT goes to minus infinity. So this is the soft region. And then in the corners, we have what's known as the soft and collinear region, where it's simultaneously at a very small angle and also got a very low transverse momentum. So how do we use this? Well, if we then try to consider integrating across this plane, integrating across lines will give us a log because the axes are log axes. So, and if you integrate across this blue line here, that's giving you a collinear log because you're integrating to small angles. If you integrate down this red line, you're getting a soft log because you're integrating down to low transverse momentum whilst keeping the angle large. And then an area will therefore give you a log squared. And we can effectively now look at computing our observables by just asking, computing the matrix element of a cross-section, for observable, by just asking how much of this plane is allowed by the observable boundary and integrating the size of that shape. and then you multiply it by the appropriate color factors. So first, let's look at the easy case, look at the loop diagram. As I already said, the loop integrates over everywhere. The observable does not constrain a loop at all because it's a virtual particle. And so that's integrating this entire gray region on the plot. And the divergences, this goes down to negative infinity. There are log divergences therefore in both theta and also kt at negative infinity. So this is a divergent contribution. If we now plot, considering first a general observable, what that might look like, that's going to now be some requirement that the observable has said you've cut out a part of a region that you're not measuring, and then you integrate everything else. So this could be this gray shape here. And it's necessary that your observable always is inclusive over the bottom line here. So you always integrate over that region because that's necessary to make the infinity from the loop cancel against the real emission piece. So that's a statement of infrared and collinear safety. Okay, so now you imagine adding the loop to the real emission contribution. Because they come with a different sign, what you end up left with is, to get the calculation of our cross section, you effectively have to integrate the loop only over the region that isn't allowed for the emission. So what's known as the complement to the observable. So the observable was saying we are measuring everything down here, and we can calculate that by just looking at the balloon plane diagram by just integrating the opposite region here with the loop. Okay, so if that's hopefully clear, let's now go on to precise the one jettiness. Now the one jettiness had this abstract definition here, but if we put in the decompose the emission angle of that particle K, momentum K that we've emitted in terms of KT and theta, this actually just ends up being equal to the KT times theta over Q, where I should have said before, Q is some hard scale. So it'll be something like the PT of the Z. It's just there to normalize the distribution. And so the region above this line is the region that is vetoed for our emission. And so we need to integrate over the loop in the region over this line to get the logs, which will give us the calculation of our observable. So tau 1 is equal to kt theta on the plane gives us log tau is equal to log theta plus log kt. That's this triangle here. And these are just 90-degree angles, therefore, of the whole way around. So it's just a square. And it's a very easy thing to add up, to calculate the area of, because its height here is just equal to log tau. And its base is, if I went across here, is log tau. And so the diamond that sits in the side is just 1/2 that log tau squared. And so we get that we can...
Sorry, one more question. So you stressed a moment ago that it was very important to integrate down to all the way to the bottom in order to capture the soft divergence that would then cancel the soft divergence from the loop. But it seems like this is missing that.
Yeah, so this is after I've done that calculation.
Oh, so this is what's left.
Yeah, so the real emission looked like this.
Yeah.
And we're subtracting off that.
Got it.
And what we're getting is this.
Great, thank you, sorry.
Yeah, so this area therefore is equal to 1/2 log tau 1 squared.
Great.
And we can now put this in, and I can add in that 0th term you mentioned, Will, here.
Yeah, great.
So that's the 1 on this side. And then plus the 1 loop correction. And we get that it's the area on the Lund plane, 1/2 log squared, which I'll use L sometimes for log just to keep it short, times by the appropriate color factors, times by alpha S over pi. And this is the calculation at what's known as double log accuracy. So obviously the coupling here is fixed. You can improve this calculation by considering corrections to the shape on the plane that is formed, saying that the observable boundary is just equal to this straight line here is the 0th order approximation to the observable. You can also then include corrections to the plane itself, such as the fact that actually the emission probability is slightly higher at the bottom of the plane because the bunning coupling runs and as a function of the transverse momentum. But that's all going to be beyond what's necessary for this talk. It turns out for this entire talk, we can do everything with this sort of most simple iteration of a Lund plane. Okay, so now how do we resum these logarithms? How do we go to all orders? Well, we just want to be integrating over more points existing in the region that the observable allows. So here's an example with 3 points, so 3 gluons emitted, and we need to be adding them up. And the general form will be this form then. They all integrate, each point integrates over this shape. So you would get the same factor of alpha s over pi times the color factors times the half log squared. But these particles are bosonic, so they've got a symmetry under exchange. So we need a 1 over n factorial for that symmetry. And this gives us the general nth term in the series, which we can sum and recognize as being an exponential. Okay, so that's the classic derivation of the double log resummation of one jettiness. So last week, I introduced the master formula for calculating observables at the LHC, and this is going to be taken as in principle beyond getting that double log right, and in particular, putting in the single log dependence on the PDS. And it looked in this general form where I said you have the partonic cross section, which is basically what we've computed here at double log accuracy, should be convoluted against the PDS, which gives us the probability to emit particles with a momentum fraction x from a proton at a factorization scale f. And I said that factorization scale was the transverse momentum scale from the initial state we were probing. Now that initial state is looking at the transverse momentum collinear to the beam line that we're probing. So if we look to the Lund plane here, we can see how we fix it. The collinear region is down the yellow lines here. And we need to be setting mu f to the largest value it can take before it gets vetoed by the observable. And so if we go along the yellow line, we find that it gets vetoed as it crosses this point where the transverse momentum over the hard scale Q is equal to log tau to the half, or the square root of the jettiness. And so this factorization scale should be equal to the square root of tau times Q. So this master formula we discussed for collinear factorization is saying that in the perturbative part of a cross section, we're getting logarithms of tau, such as we compute on this slide. But from the collinear evolution of the PDFs, they're actually a function of logs of square root of tau. They're existing at a higher scale, a higher transverse momentum scale. It's worth pointing out that this is a simplification. You can write it in this form. The full factorization that actually takes this form, again introduced by Stewart et al. But I'll just highlight that this is the full factorization. There's a hard function here. This describes the perturbative evolution. This is known as a jet function. This is also effectively a part of the perturbative evolution of the final state. The soft function is also part of the perturbative evolution of the final state. This generates our double logs. And then the initial state are described by these two beam functions, these B's. And if we look at what they contain, they actually contain the PDF evaluated at the scale I just said, but they just also have a perturbative matching coefficient in front of them. So the simple story on this slide does actually hold to an all orders derivation, where this is now accurate up to corrections in 1 over the Q squared. And this all can be summarized effectively, this entire complicated formula for our perspective is requiring the following log structure. There is an exponential piece that we just computed, and it's multiplied by corrections, and these corrections have to have this form. G0 is the first correction, and it has to be a function of just alpha f times log. There's no log squareds in G0. All the log squareds are in the exponential. And then plus alpha s times G1, also a function of alpha s times log. So this is an alpha s suppressed term. And then so forth and so forth. So we call this G0. This is the leading log piece. G1 is the next leading log piece. G2 is the next leading log piece, because they're each suppressed by powers of alpha s. And this factorization is telling us that within G0, we should get terms that look like the PDF evaluated at the square root of tau times Q. And there's no extra double logs going around. And this factorization formula by Stewart et al. Was used to compute the observable under the assumption that the factorization holds at next to next to next to leading log by Aoli et al. And that's including up to G3, what I didn't even put in this formula. So that's 3 powers of alpha S suppressed. So in principle, that's an exceedingly accurate calculation. How would factorization breaking look if it were present in this formula? Well, a really obvious sign of factorization breaking would be if there were terms that looked like alpha S to some n times by a log to some m, where m is larger than n. So for instance, if we found an alpha S to the 4 log to the 5 that doesn't have this functional form, that would be a very obvious breaking of the factorization, especially if that log depended on the PDF. That cannot be described by this factorized approach. Okay. So let's pause jettiness for a brief bit and talk about collinear factorization breaking in another observable way it's now been very well understood. And that's the superleading logarithms in the gaps between jets observable. Now, this is basically an observable where we say we've identified 2 jets in the final state, and we put a cut that all of the radiation between the jets, between some angular separation separating them, is below some threshold value in KT. So the jets are separated by some rapidity, y, and there is a cut, which we call Q0, which the KT in that rapidity gap between the jets has to be less than. Now, this observable was thought to factorize in a very simple form by Oderda and Sturman in 1998, and it has this very simple form here, which again is PDF factorization times what's known as the perturbative cross section, which was sigma hat before, which has been now refactorized into a hard function. This is just like your tree level 2-to-2 scattering times by a soft function, which will describe the possibility to radiate a gluon into that gap region, which we're vetoing. And importantly, in this case, the PDFs are evaluated at Q, which is the scale of the partonic cross-section, the center of mass of the partonic scattering. Now, it was very rapidly observed that this factorization doesn't hold. In fact, it contains non-global logarithms are present in this observable, and that's missing in this factorization. But that won't be the focus of this talk in particular, because that's basically a statement that you can't factorize H and S apart from each other in this way. In 2006, it was also noted that this observable contains superleading logarithms, which basically say you also can't pull the PDFs out in this way. So not only can't you not split H and S, you also can't pull the PDFs out. So it's altogether unfactorizable in this form. What does this look like diagrammatically? Well, a general calculation of a process might look like this, where this is introducing a color scheme I'm going to use from this point on. Things from the initial state will be in blue. Collinear radiation is going to be in green, and soft low energy radiation is going to be in this violety purple color. And factorization for this observable will be saying that you can pull out the PDFs and all the collinear radiation associated with them, disentangle them from these soft loops, and in doing so, define your PDFs at the highest scale in your problem, the center of mass of the partonic scattering. And this requires that you have the following functional form for your resummation. Breaking this factorization would look something like this. We've got a green gluon, a collinear one, interleaved with a soft one, and they can't be pulled apart because some other things are going on, which I've got in red here, and these are going to be what are known as the Coulomb or Glauber loops. Let's look at this on a Lund plane again to see exactly how this is looking. Calculating this observable at one loop, is very easy because we have that simply that outside of the jet, we're vetoing everything below a scale Q, transverse momentum scale Q0. So that's this horizontal line on our one loop plane. If it's in the gap region, and the gap we're taking to be relatively small, we don't want to be resumming logarithms of the gap width, or not logarithms of gap width, we don't want to be resumming the gap width. So the gap width Y is like order 1. So we have these vertical bands define the gap width, which is this gray area here between these two jets. And as I emphasized earlier, you calculate at one loop on the Lund plane by looking at integrating the loop diagrams in the region where the emissions are not allowed. So for this observable, we're not allowing emissions into the gap between the jets when they have a transverse momentum above our threshold scale. And so that's this small sliver here. That's in the gap. This gap has width Y, and it's above our threshold on the transverse momentum Q0. And so you can see that this observable is a single log observable rather than a double log, because I said before, an area on the plane gives you a double log, whereas a line gives you a single log. And this is effectively just integrating down the y-axis. The width is just y, so that's not a logarithm. Now, if we do this with two gluons, we just get the same thing squared divided by a half. That's the, again, the exchange symmetry because they're bosonic. That's the 1 over n factorial. But if we go to 3 gluons, we get an extra term. And this extra term is coming from these Coulomb or Glauber exchanges. So we get what we'd expect, plus this other term, which depends on this factor I pi. So it's clearly complex. Now, let's look at this a bit more carefully, what's going on. I introduced last week that we have this color basis independent notation for writing an emission of a soft particle. And we can use this to write down completely generally the full one loop singular structure of any sort of loop dressing a process. So this is a cross section at one loop, and it's equal to, this is the matrix element with note at tree level. And this is a matrix element at tree level. And we're sandwiching in between this color charge operator with a kinematic factor, which corresponds to a loop being exchanged between two legs. So that's the charge of particle I, that's the charge of particle J. Then we have this color charge operator, which is diagonal. It's a loop that goes from I to I. And then we also get a complex phase, which corresponds between only this TS squared is saying that it only goes between initial state legs. So I've called the initial state A and B here. Now, the reason people ignore this complex phase, and I didn't mention it earlier or last week, is because at one loop, you get a minus I pi from the amplitude and a plus I pi from the conjugate amplitude, and the two exactly cancel. And that's actually why we don't see it until we get two of these complex phases adding up. But the important point with these complex phases is this color charge operator does not commute with any of the other color charges involved in this diagram. Last week, I showed that you can factorize collinear from soft by commuting the collinear charge past the soft charge. And that's this term here corresponds to collinear emissions. So looking like a self-energy diagram. And this term here is soft going between two legs. And as I said last week, we showed we can pull these apart and factorize them. Nothing commutes past the I pi term. And so you need to have that these cancel organically, effectively by having this, you get an I pi from the amplitude and a minus I pi from the amplitude and a plus I pi from the conjugate amplitude. If it don't cancel organically, you're going to find that everything becomes more problematic in the calculation of your observable. So let's put these all on the Lund plane and kind of have a slightly more complicated understanding of the Lund plane now. So I previously said the boundary here is collinear. In the middle, we've got soft. bottom left and bottom right, we've got soft collinear, and all the poles live at the bottom. We can now also put on the Lund plane what the basic color structures are. So down these collinear boundaries, that's where we're seeing this diagonal term, which describes collinear physics. So the boundaries here are color diagonal and simple. In the bulk down here, where we've got soft, this is where we've got the off-diagonal stuff. This is where everything's complicated. And this is over this entire area that's away from the boundary, but still down the y-axis. And then only down the y-axis, we have the IPi terms, because if you notice, the IPi terms only integrate over log kt. They don't have an integral over momentum fraction z or the angle of the emission. So the IPi terms just go down the y-axis. The soft terms go anywhere in the bulk that doesn't touch the yellow lines. And the collinear terms then go down the yellow lines, and there below is very simple. And with this, we can now do gap between jets at fourth order. So we've now got 4 gluons being emitted into this region. We've got two IPi terms, which are in red, two of those, and then 2 soft terms, which are in the violet. And here's the problem. This top soft gluon, if we consider integrating it outside of the boundary, the gray region, that's the region where the loop was meant to perfectly cancel against the emission. And so it wasn't meant to be contributing to our observable. But because these IPi terms don't commute with the collinear charges, the loop isn't cancelling perfectly in this region with the observable anymore. Sorry, the loop with the emission. And so actually, you now get that this entire region, your gluon can be emitted into, but it's going to be proportional to a color charge, which is given by this commutator. And so because it's a commutator color charges, it's suppressed by powers of NC. And then below the line again here we're completely inclusive over everything. And because we're completely inclusive, all the IPi terms actually cancel and everything cancels completely fine. So you get that there are no extra poles going on. All the poles live below the line, but we've got a log to the 5 term. And that's because we got these 2 reds produce a single log and also a factor of IPi each. So single log times IPi squared. This violet also is a soft that produces a single log times the gap width, which is y. But then the green one that started off up here is integrated over this entire triangle and gives you a log squared. So you get y times IPi times log squared times now a complicated color factor, this calligraphic C, which is equal to all these commutators I've written down here. Okay, so this is a superleading logarithm because in this observable, I previously stated that all the logarithms have the form alpha s times y times log, whereas now we've got something which has a contribution that looks like alpha s times y times log squared times other alpha s times logs. So this is an even more higher power of log than you would have expected. And so hence the superleading name. And in particular, these superleading logs exist because of the non-trivial color associated with the measurement and associated with the complex phases of the loops, these Coulomb or Glauber phases. Now, recent developments have shown that you can actually still write down a much more complicated factorization for this observable that doesn't look like the QCD master formula I wrote at the start. You now have the PDS evaluate at a lower scale, and using this factorization, they have been able to resum these effects. And what they've found is that even though this effect is happening at 4 loops, so at 4th order, it actually, because the logs get large, can be a very large effect. And in this observable, they're finding for, these are quite moderate gap widths. 3 units in rapidity, they're finding you can get up to a 15% effect over the calculation without these present. So this is an important effect, despite the fact it first starts at 4 loops. If there's no questions on that quick summary of gap stream jets, I'm now going to return to jettiness and use this intuition for jettiness. So this was gap stream jets, but now let's grow the gap. Let's imagine you let y get large. So previously it looked like this, really narrow slice in the middle. Now we're growing it. And that means that this soft guy can integrate over the entire gray area. The red ones, they're the phases, they still have to go down the y-axis, and you still have double log from this green area as well. And if we do that, we can ask ourselves, what is the largest value of y that we can take that would maximize the effect of the superleading log? If you took y too large, you actually squeeze the green region into nothing. So that actually kills the superleading log. So there's a balance. There's a maximization point where you have that y is as large as possible, whilst the log is also as large as possible. And that turns out to be when you set y is equal to 1/2 of log q naught over q, or in other words, log the square root of q naught over q. And in that case, you get color factor times alpha s over pi. So these should be alpha s to the 4 there, not alpha s. I've just noticed that's a typo that was possibly present on some previous slides as well. Yeah. So you get color factor.
The par 5 you had in the previous one was probably accompanied by
Yeah, I had the mistake here as well.
4, right?
So yeah, that should be a power 4 here.
Yep.
And you also should have a power 4 on this slide here, power 4. So yeah, so what we now have is you get the exact same structure we had before, same color factor, but you now have alpha s to the 4 log to the I pi squared times the original log to the 5 times another log, because y has become a log. So it's actually alpha s to the 4 log to the 6. Now, crucially, there's actually nothing that causes this log to miraculously vanish. But it's very counterintuitive, because once you've got an extra double log there, you typically would imagine that means you're coming close to the yellow boundary where the color is diagonal, and so the superleading log should cancel. But let's pause a discussion of exactly why this log survives until a bit later on, and just recognize that I only need to slightly modify my diagram and I've got the jettiness observable. If I just make this line here diagonal, this is now jettiness. And instead of it being log q naught over q square rooted, it's just log a root of tau. So this would lead us to believe that there could be an alpha s to the 4 log to the 6 in jettiness, unless something miraculously cancels it. And that miraculous cancellation will have to be from doing the color algebra. Okay, so if the miraculous cancellation is to test this properly, we actually just need to go ahead and compute it carefully, and this means getting our hands dirty and doing the full color algebra. I don't want to go into this in too much detail, but you can write down the general cross-section in the following form. This is the matrix element for the emission of a first collinear gluon, the one that becomes this green space here. This W is a color diagonal piece that doesn't really contribute to calculating a superleading log. And then this color trace is the calculation to all orders of these red, violet, and red gluons. And it turns out when you do this calculation, you very, very rapidly find that the color does immediately vanish if one of these soft gluons is emitted into the region with a higher transverse momentum than the collinear gluon. So in the previous slide, I was saying that by analogy to gap stream jets, it could look like this. In actual fact, it looks like this. You need that the soft region where they're emitted is below the top of the collinear region. Otherwise, the color does quickly vanish. Okay, so this is now what the phase space we're trying to integrate our 4 emissions over. We've got 3 softs, where 2 of them are Coulomb in the gray region and 1 collinear in the green region. And we do this we expand to 4th order this matrix element I've written here, which gives you this full expression here with all these integrals over all the different transverse momenta and color factors associated to each one. And long story short, you find out that everything evaluates to the same color factor up to a minus sign. Some diagrams have a different minus sign on the color factor than other ones. And because of that, everything cancels other than the 4 diagrams that I've drawn here. And they all have the same color factor up to minus signs and plus signs, which I've put in between each one. And so what are these diagrams? This is a soft linking the initial state to the final with some coulombs linking the initial state to the initial state, and then a collinear before all of that. And this comes in with the opposite sign color factor to the exact same contribution, but where instead of the soft linking the initial state quark to the final state quark, it's linking the initial state quark to the final state gluon that was radiated off the initial state. And then you've got the same thing now, but for the other side. So now we've got a soft linking the initial state gluon to the final state quark, and then a soft linking the initial state gluon to the final state gluon. Okay, so turns out these 2 diagrams exactly cancel kinematically because if they've got the same color factor, the only thing that remains is caring about the phase space of the particle of the emitted soft gluon, this violet one. And because you can do a Lorentz boost that transforms the topology where this outgoing quark is going slightly out of the plane, out of the beam axes. You can do a Lorentz boost to a frame where it's in the beam axes, and instead this green gluon is going out of the beam axes. And the end result has to be Lorentz invariant. They both cancel each other exactly. So all you have left is these 2 diagrams on the right now. So let's plot their phase spaces on the Lund plane and calculate them directly. This one on the left is exactly what we've been doing already. This one is, so it's the Lund plane drawn as normal. This one on the right, though, actually looks quite different. And this is for the point that Will mentioned earlier, that this KT has to be the transverse momentum relative to its parents. In other words, it's the dipole frame transverse momentum. And the dipole frame for this green gluon, which is collinear to the initial state, and the blue gluon, which is in the initial state, is a very large Lorentz boost from the lab frame. And in that frame, it distorts our observable boundary such that almost the entire phase space is vetoed by the measurement. And this is intuitive because if I were to draw on the cones we're vetoing, we're saying everything needs to go down that cone in the beam axes. So that's what I had drawn on before. There was one on the final state here as well. All the longitudinal momentum needs to be down there. And we also had one on the initial state here from that beam axis. And you find that the dipole is entirely subsumed by the cone. The green has to be inside it, the blue's inside it. And so you're boosting to a frame where the cone eats the entire phase space. And so these, you then calculate the log and they mismatch. They don't cancel. There's a minus sign between the 2 of them. But this one on the left gives you a different log to this one on the right. And you add them both. And what you get left over is the following. You get a log to the 6 in tau 1 times by pi squared times by alpha s to the 4. I've not got the typo on this side, thankfully. Times by a color factor, which is suppressed by 2 powers of NC. That comes from that complicated color trace I previously mentioned. And what's quite astounding is this very severely violates the exponential form we're expected to get for this observable. Again, sorry, this is a typo again. This should be a log squared here over 2. There we go. That was the wrong exponential form. That was the gap between jets down there. It should have been the jet in this one. But yeah, so this drastically violates our expectation from factorization because it depends exactly on the PDFs, and it depends on the PDFs evaluated at tau times q, not square root tau times q. And it depends on a log to the 6 times alpha s to the 4. So it's not just super leading with respect to DGLAP, as was in the gap between jets case, it's super leading with respect to DGLAP. It's 2 powers enhanced. But it does ask the question though, why does this log not cancel? And this is what I pointed to before, because we typically imagine a log squared should be color diagonal. And so we'd have thought a super leading log should be impossible. And the answer can be understood in a variety of different ways. But it's easiest seen on the Lund plane, because the important point is this gray region, which we're integrating over to get our extra log squared, is logarithmically large. It's an area on the Lund plane, but it actually never intersects the collinear boundary. It's got 0 dimension on the boundary. It touches it at a point. So it actually never goes collinear. So what this log squared is, it's not a Sudakov log. It's not associated with a 1 over epsilon squared pole. It's a soft log that's associated with a 1 over epsilon pole with a logarithmically enhanced phase space volume. And that's why it's able to have this complicated structure, color structure, that prevents its cancellation, but also can be a large log. Now, you can show this in a variety of other ways. When I wrote down how you calculate this observable here.
Let me just ask
yes,
very super naive question here. So it's the phase space size that makes it escape power suppression. Is that the?
Well, there is no power suppression here. This is actually at all. So actually, in terms of power suppression, this diagram on the right, this boosted forwards one, is actually power suppressed. So actually the end result I'm showing you here is actually just this diagram. That's the only thing that survives and gives you the log.
The other guy is, oh, okay. So that guy
this one ends up being power suppressed, yes.
Yeah.
This one, so this one actually ends up being something like root tau times log to the 4. And this one's log to the 6. And so obviously they don't cancel and you get a log to the 6 left over.
Yeah. Okay.
And this one on the left has to not be power suppressed, because actually if the coulombs weren't there, it's exactly what gives you one of the just leading log pieces. Yeah.
So it has an entirely different source for the logarithm. That's just
yes. But so yeah, this is. But the important point, though, as I said, is it's not a Sudakov log that's giving this log squared now, because of the fact that it's integrated in just this triangle here. If it were integrating like along this axis at all, then it would be a Sudakov log, and you'd expect the color factor to cancel. And yeah, and you can see this again, like I say, you can see it on the Lund plane. But you can see it actually more algebraically by, if you return to this is the formula for computing this logarithm. And this is a amplitude level Sudakov factor, which you could also attribute in a sort of an EFT language to being a Wilson line of a soft radiation going down each of the hard legs. I haven't collinear subtracted it here. If you did a collinear subtraction, as will be seen in the paper we're going to be putting out on this topic soon, it turns out they all perfectly cancel from a calculation. So it's entirely independent of collinear subtractions. Again, indicating that this is a soft log with a logarithmically enhanced phase space volume.
Okay.
And so, yeah, so what does this mean though? You have a log to the 6, but looking at this Lund plane, it is not associated with a 1 over epsilon to the 6. It's still a 1 over epsilon to the 4. It never touches this collinear boundary, and it's shielded from the low boundary on KT by the inclusivity. So PDFs can still be defined, they just have to be defined at the low scale, such as we found on the previous slide, tau q, not square root tau q. Okay, so that leads me to my conclusions, which is one, jettiness does contain a super leading log. In fact, it contains a super leading log. So maybe it's not quite the optimal simple observable that people think it is. But crucially, the log does not touch the pole structure. So PDFs can still be defined. They just have to be defined at a much lower scale than was anticipated. The resummation of these logarithms looks to be exceedingly tough. Unlike gap stream jets, where you could resum them whilst only considering a single soft wide-angle emission, and that's been crucial to the work of Becker and Neubert and et al. To do a resummation. Here, because that soft emission is now giving you a log squared, you have to include both an arbitrary number of collinears and an arbitrary number of soft. And how to include more softs is an unsolved problem. So you can't immediately resum this using the framework that's already been put together by Becker and Neubert. It looks to be a whole magnitude of more difficult problem. However, numerical codes may be able to do this, such as Cvolver or Deductor, if they're able to manage that. But it's worth pointing out that these numerical codes also do really struggle once you have to go to very high emission multiplicities to get these like full color results. I think the recent Cvolver paper where they showed these impressive display of 50 different observables all calculated to full color are still limited to only being able to do 7 to 8 full color gluons. So they can only look in the region where that matters for the observable. And when you're considering an effect which starts at 4th loop, only going up to 7 gluons means you're only really including 3 loops worth of information in the resummation, which I don't think in many cases is ever really completely enough to resum a result. I think typically you need to span an order of magnitude in the number of loops you're considering. So it would be very interesting to see if numerical codes do in fact manage to resum this or if they struggle to converge. So yeah, so that's everything. Thank you very much for listening.
Okay, so super duper. Any questions from the audience where I'm not going to turn around, where I will turn around slowly? Yep.
Yeah, so there are a couple of things. So now you have to do 2 things, right? You have to go down with the scale in your PDFs. That means in order to have anything perturbative going up into this, you need to look into a particular part of phase space.
Yeah, so I think this would motivate a new factorization in the same form as Becker and Neubert. So it should look like d sigma d tau is equal to something like the W at tau times Q, convoluted with their calligraphic H, which includes the entire perturbative cross section and all the resummation at tau times Q.
So you have to go
and then
with the perturbative.
Yeah, you need to go further into the inframed with the perturbative because it'd be at tau times Q, it'll also be root tau times q for the perturbative this beam function stuff, because when the coulomb are turned off, you still have the full structure that was there before. So you still need to have the beam functions at this scale, and also at q for the hard scale. So this is now you're stuck in a situation where you need to factorize at this very low scale w onto this very complicated hadronic tensor, which will refactorize into some like color factor, I don't know, call it C, convoluted with PDFs at tau q.
So in terms of effective field theories, you would have to layer them 3D.
Yeah. Yeah, so exactly. So this isn't in terms of single scale matrix elements anymore. Like this W is just at tau q, and that's got the PDFs, but this still is not refactorized at all. This is a 3-scale matrix element because it depends on both the soft scale, the collinear scale, and also the hard scale.
Fantastic.
And how you factorize H is entirely unknown, I would say, and it's in H that this logarithm should be sitting, where the PDFs here now should be sitting in the W at that low scale.
Yeah.
Yeah, so it certainly looks to be more complicated.
That sounds like mega homework.
Well, I do think the basic framework for handling this that Becker and Neuber have looks like it could be adapted to this form. Like it's still the same thing of their W and their H, like in their EFT they've set up. The problem is that at least within the techniques they've currently developed, where they do everything by effectively trying to compute H in this single soft Gluon approximation. That's now not going to be tractable anymore. They're now going to have, so I think their framework is still in principle the right one to write down the starting point, but at least a priori it looks impossible to solve without a lot of insight beyond where the current frontier has got to.
So maybe a nitpicky question, but when you say factorization is broken, so I think of factorization in the Collins and Sturman sense, that you have some idea of the power law in Q that the result is scaling with, and that logs are free. Logs are painful, but are free. So I would have, so in
this sense, Collins-Soper-Sturman factorization, it depends on how you understand it. It's both broken and not broken.
Okay.
If you understand it in the traditional sense, where Collins-Soper and Sturman themselves were applying this, for instance, in like Drell-Yang, or where they were looking at PT distribution in the final state, their leading power factorization into PDS and a perturbative thing requires that the PDS both factorize at that power, and also their natural scale is the collinear scale because they follow a DGLAP evolution. That's required for consistency in the factorization. Otherwise, if it's not following a DGLAP evolution, they're not a PDF. And what this is saying is that you can still do that Collins-Soper-Sturman factorization, but the PDF scale has to be much lower than you expected. It has to be at the soft scale. And up to that soft scale, they follow a DGLAP evolution and they're a traditional PDF. Above that soft scale, the evolution isn't DGLAP anymore because it needs to somehow know about these log to the 6 terms that are coming out. And so in that sense, it's not really behaving like a PDF anymore.
Yeah, that seems like something different to me, but and I think sort of the language is not the most important thing in terms of like whether we call it factorization or not. But I think the thing that I guess that particularly concerns me is that so Collins et al., at least the way that I think of what they do, is that they think very carefully about whether infrared singularities will change the power law scaling in Q for the overall result. And they claim that they can have certain proofs, like they can isolate singularities, they can consider very carefully the amount that those IR divergences can contribute in terms of anomalous scaling in Q. So
Yeah, and so but the important
when calculations were done looking at this one jettiness, you know, was there this consideration of the pinch singular surfaces and all of these various things, and then really made sure, because it seems like, you know, the way that this has been, the way that I've taken what you're saying, it's like, oh, there was a surprise extra logs here, and that's interesting. But was it something where, you know, like the usual analysis, the factorization analysis, missed this in a way that one would expect the usual factorization analysis to miss this? Or was there something even worse happening that I'm not picking up on?
So the thing, yeah, so it's a very multi-layered discussion here, really, in terms of both how the initial factorization for this observable came about. So the thing with Collins-Open-Sturman factorization is it's only proven, and in fact only writable in terms of it all being determined in terms of Q, power corrections in Q, if you're sufficiently inclusive such that what you're measuring is effectively single scale, right? So you can expand in Q, and that's what's measuring. So that's why it's like for Drell-Yang or like the Z boson PT distribution, because you're measuring something that's a color singlet. So the QCD matrix elements are single scale or two scale or something like that. I think it's two scale in terms of the ZPT, and it factorizes onto a collinear scale on a soft when you pull the PDFs out. There are basically no proofs within the framework of Collins-Open-Sturman factorization for completely generalizing it to exclusive measurements, or like where you are properly measuring on the colored final state, such as the jettiness is doing. Instead, how these end up working is they kind of use a hybrid of, you know, if you're sufficiently inclusive, Collins-Open-Sturman holds. And so you could look at very low scales and use the Collins-Open-Sturman style factorization. And then also you can define an effective field theory, which you think captures all the QCD singularities within a given leading power, and look at how that EFT factorizes as you compute the full thing. And that's how you get to this factorization that was Stewart and people wrote down for jettiness here. Right, this is a factorization that's derived in SCET1 for the observable, and it's based on assuming that you derive SCET1, which assumes that these Coulomb and Glauber effects aren't present. And the assumption that they aren't present is based on the fact it's known in Collins-Open-Sturman if you're sufficiently inclusive, they cancel. And then the sufficiently inclusive is really the problematic term. And then you say, okay, these effects aren't there. I can now define an effective field theory for QFT, or QCD, sorry, and look at how that effective field theory factorizes for this observable, and you end up in this result. And really the statement that is therefore being made is that you're wrong to think the Coulombs and the Glaubers cancel. You've got the wrong effective field theory getting to this factorized result. And it's because you're trying to apply Collins-Open-Sturman factorization at a scale where it doesn't hold, at the collinear scale. It should be applied at the soft scale. And then you need to define a better effective field theory which captures these extra singularities from the Coulomb and Glauber phases. And so, you know, when people write down this factorization formula, they would say, like Colin, Stope, and Sturman, that this holds plus, I think, 1 over q squared corrections. But it's up to those corrections given the EFT you're working in. And then it's your assumption that that EFT is the right one for QCD. And effectively, you could say this result is saying that, yeah, it's the wrong EFT to compute this observable info.
Yeah. Okay, so this smells like a perhaps more rigorous, but in a similar spirit to energy loss, where one says, you know, I think that things are going to work out, and we're going to calculate things and see if there are issues that emerge. And you've shown how, you know, the naive expectations were defied here.
Yeah, and I think the increasing knowledge that we have of what this actually means in terms of Colin, Stope, and Sturman is it's always been a statement that Colin, Stope, and Sturman factorizations up to power suppressed terms in Q holds given a sufficiently inclusive measurement. And what that's where I think you can increasingly say we've learned is that that statement of sufficiently inclusive really says you have to be completely inclusive over anything that's colored. And so you can measure effectively exclusive things on color singlets. So like you can do Z boson PT. You could try and identify a 2-jet event by trying to find 2 associatedly produced Zs in weird directions and do constraints on those 2 Z things. That it's not something you'll ever measure because the cross section will be so tiny, but that in principle would have the simple factorization Colin, Stope, and Sturman form. But once you're trying to do an explicit soft sensitive measurement on the on which is sensitive to the structure of the hadrons of the QCD in the final state, then really Colin, Stope, and Sturman only really holds for radiation that's in this part of the Lund plane. Everything above it, all higher transverse momentum scales, you need to evolve up from that Colin, Stope, and Sturman factorization with a much more complicated evolution.
I'm sort of not surprised at all that something that has color in the final state has singularities, because I could always emit gluons, right? But I'm sure the people that were doing this were very smart. So was there some reason why they thought that that wouldn't happen?
Well, no, they had singularities in the final state as well. Like the factorization theorem here, if you neglect Coulomb stuff, these all depend on the renormalization scale, each of these operators here, because every single one of them diverges. And it's the very non-trivial statement of this factorization that all singularities cancel once you include the full thing. Same way Colin, Stope, and Sturman has their initial state fit singularities in the PDFs, and also initial state singularities in the partonic cross section, and they cancel between each other for a sufficiently inclusive measurement. And the point is that so this is a completely consistent factorization where all the singularities are each one is individually singular, but all singularities cancel. But it's built on the assumption that the EFT does not contain Coulombs and Glaubers, which generate new singularities and new logarithmic terms which are missing in this factorization. And they're what effectively the logarithm from that is what I've computed. And what I try to stress is a very weird logarithm, because the singularity that they're missing is they're missing something that's a 1 over epsilon to the 4 that has a log to the 6 with it. So it's a very weird singularity that they would never have, I don't think anyone would have seen coming. Like we went into this project expecting to find a log to the 5, not a log to the 6.
Yeah.
Surprise.
Yeah, exactly. We didn't expect to be writing a paper on super leading logarithms.
Very good, thank you.
That was fantastic.
Any last questions from the audience? Then let's thank Jack again.
Thank you for having me.
Bottom,
Down,
bottom,
down,
bottom,
bottom.
right.